Before we discuss what a conservative vector field is, we need to know the different kind of curves in space, in R2 and R3. So if we have a curve like this, let me draw them with black. So I'm going to draw three different kind of curves here. I'm going to draw this one, and then this, like that, and then this one. Okay, so this curve is a closed curve, and it's kind of easy to see why it's closed. It's simple. All right, it's closed and it's simple. Okay, I'll come back to that. This is not closed, but it's simple. This is closed and it's not simple. This is not closed and it's not simple. So with this, we can give a slight, a loose definition on what closed mean. Okay, closed and simple mean. So these are our curves. So if we call each of this curve C. So assuming C is a curve and C is represented by R of T in R2 or R3. For T between A and B. All right? So closed, the word closed means that it implies that R of A is equal to R of B. What do I mean? So if this point is A, right, and say we have a counterclockwise orientation, okay, so if you have, if you have the value of A here, okay, then the same value is what you're going to get at B. Okay. So it's a closed curve. If you parameterize it, R of A is the same thing as R of B. Okay, so another explanation or another thing we need to think of is what it means to be simple. I think it's easier to explain what not simple means. Not simple means that there exists T1 and T2 such that R of T1 is equal to R of T2, right? But at the same time, T1, it's either T1 or T2 neither of T1 or T2 is equal to A or B. So what does that mean? So R of A is somewhere here. R of B should be somewhere here. All right? All right. So this curve, for instance, is not closed. It's obvious to see why it's not closed now. But it's simple. It's simple because there is no crossing, basically. So any other if this is r of t1 and this is r of t2, it's obvious to see that r of t1, for any t1 and t2 other than a and b, r of t1 is never going to be equal to r of t2. The same thing can be said for the first curve. However, in this case, this curve is closed because if we had, say we have a positive orientation like this, then if this is r of a, this is where it stops and this is where it ends, this is r of b also. But at the same time, we have a crossing over here, and this crossing indicates that there is a t1 and there is a t2 such that r of t1 is equal to r of t2. Okay. Now, it's quite easy to now see why the fourth curve is not closed and not simple. All right, so these are the types of curves we are going to encounter in this section. All right, the next thing I want us to do is to look at different kinds of regions. So we have, let's look at a region in R3. Think of it as a region in R2 also. So this region, I would say this region is simply connected. And I'll explain later on. Then we have another region all right. This is connected, but not simply connected. Not simply connected. So we have connected, have simply connected. We have connected, but not simply connected. Let's look at another region. This is a region made up of two regions. These regions are not connected, but simply connected. Okay. Now, let's look at this region. This is a region made up of another two regions. This region is not connected and is not simply connected. All right. So a simply connected region, if you think of any 2 points in those regions, you can always draw a line, can always draw a straight line between those 2 points. All right? That's simply connected. Connected, but not simply connected, is you cannot draw a line, a straight line. You cannot draw a straight line, but you can always find a path that goes between the two curves. So you can always find a path. If you're at a point P and there's another point Q, there's always a way to get from P to Q. Now, simply connected, right? If you have a not connected, but simply connected. So not connected, this third one is not connected. It's not connected because we can find 2 points that we can't get to. You know, there's no way to go from the first point here to the second point. However, if we have, there are a bunch of 2 points inside that we can, if we restrict ourselves to a subset of the region, then we can always find, for every 2 points in the first region, for instance, we can always find a straight line. All right, so that's simply connected. However, the whole region is not connected. Now it's quite easy to see why the third one or the fourth one is not connected and not simply connected. If you have questions, email me or ask me in class. Now, let's look at a conservative vector field. So a vector field, F, is said to be conservative if there exists a scalar function phi such that f is the gradient of phi. Okay. All right, I think we encountered such a thing before. If f is a gradient field, then it is conservative. Okay. All right. Then, how do we find that? How do we approve, or how can we show that a vector field is conservative? If we let F be the vector field, F, G, H, let it be a vector field in, F is a vector field in a simply connected region. Simply connected region. Now we know what a simply connected region means. In R3, right? F is conservative if and only if the following is true. df dy is equal to dg dx. df dz is equal to dh dx. And dg dz is equal to dh dy. All right? So this is the condition for being conservative. And I'm going to explain this with an example. Don't worry. Okay. So let's do some examples. So we want to determine if each of this is conservative. So the first one is the vector field f of x, y, z. And f of x, y, z is 2xy minus z squared and then x squared plus 2z, and then 2y minus 2xz. So we need to check a bunch of things. We need to check df dy, and we also need to check dg dx. So think about it. Why are we doing all these things? Or is there a pattern to this? Obviously, this is a theorem, but we don't have the time to prove it. So look at this, right? So if you have this function, this is f, g, and h are functions of x, y, and z. But at the same time, this is a gradient. So f is the derivative with respect to x, y is the derivative with respect to y, g is the derivative with respect to y, and h is the derivative with respect to z. So what are you doing? You really have to check the derivative. You want to check the derivative df dy, right, is the same thing as dg dx. So you want to flip, you want to switch their variables, right, to get that. Okay? And then you do the same thing with f and h. You switch f's variable, would I say, corresponding variable with that of h. So you also do df dz, is it equal to dh dx, and so forth. So let's try df dy. Df dy is equal to 2x, right? Is this equal to dg dx? Dg dx is also 2x. So yes, dg dx. So we have that down. Then let's look at df. We have to check now df dz. Df dz is equal to negative 2z. Is it equal to dh dx? Actually, yes. So this is dh dx. So we're good. So this is our f, this is our g, this is our h. So lastly, we need to check df, or let's do dg dz. Is it equal to, dg dz is 2. Is this equal to dh dy? Yes. So this is true. So if one of them is not equal, if one of them doesn't hold, then that means the whole condition is violated and the function is not conservative. So f is conservative. Now, let's try another one. B. Let's try f of xy. The vector field is e to the x cosine y negative e to the x sine y. Okay? So, now, this is in R2. We only have x and y. So that actually makes it easy. So all we need to check is df dy, is it equal to dg dx? That's all we need to check. So let's do df dy df dy is equal to negative e to the x sine y. Now, is this equal to dg dx? Actually, yes, it is. So this is our f, this is our g. So it is. So this means we have another conservative field. So f is conservative. Okay? It's not liberal. It's conservative. That's not what it means. That's another kind of conservative. All right, let's look at a third example. Let's do f of xy is equal to x minus y, I, so I'm switching to a different kind of notation, plus x minus z, j. So let's do df dy. Df dy is negative 1. Is this equal to dg dx? Dg dx is 1. So this is not equal. Therefore, the vector field is not conservative. F is not conservative. All right? Now, let's go back to the definition of what it means to be conservative. The definition means that f is conservative if there is a function, phi, such that the gradient of phi is equal to f. Okay? So with this definition in mind, so let's copy this. With this definition in mind, let us do another example. Okay? That's the definition we're going to be working with. Move it over here, move it there. Okay. Oh no, something just happened. That's not good. That's not good at all. Okay. Where is my copied and pasted stuff? I'm mad now. All right. So let's go do it again. iPads. Let's copy this. Paste it here. This is the definition we're working with. How far can we get with this? What would you do with this? All right. So, second example, we would like to find a potential function phi okay for the conservative vector field f of xy equals 3 plus 2xy and x squared minus 3y squared. You want to find the potential function. All right. Now, so it is true that f is conservative here, which means that f is the gradient of phi. So that means that this is the partial derivative of phi with respect to x, and this is the partial derivative of phi with respect to y. Okay? Or let's write it like this. It doesn't matter. This is d phi dx, d phi dy. Okay? You can use either. All right. So let's first recall that. First, recall that d phi dx is equal to 3 plus 2xy and the phi, oh no, dy is equal to x squared minus 3y squared. All right? So we recall that. So if that's the case, x of y, a phi of xy, is equal to the integral of 3 plus 2xy dx. Okay? All right? So if we find the integral, we're going to get our phi of x. At the same time, phi also, phi of xy is also the integral of x squared minus 3y squared dy. All right? So if this is the partial with respect to x of phi, then if we take the integral with respect to x, we better get phi. If this is the partial of phi with respect to to y, if we take the integral of phi with respect to y, we better get phi. So, but let's see, what do we have now? So that means this is equal to 3x plus x squared y, right? And what do we get? And then plus, we can say this is plus a constant, but this constant of integration will just be a function of y because our integration is with respect to x. So it can't just be a regular constant. Our integration is with respect to x, and it's a function of two variables. All right. So, and in this case now we have x squared y minus y cubed plus a function of x. Again, since we're taking partial with respect to y, that means that our we treated x as a constant. So any constant has the possibility of being a function of x. All right, now compare these two things. Our claim is that each of these two functions is equal to phi of y. So look at this. If that's the case, we can correspond terms, right? This term is definitely this term, right? These two terms are definitely equal to each other. So we're left with two terms to correspond to each other. So if we have a d of x here, that means this d of x must be equal to 3x, and this c of y must be equal to y cubed, since the two functions are equal. So if that's the case, our phi of xy, the potential function, will be equal to 3x plus x squared y plus dx plus c of y, which is y cubed. Okay? So that's the function we're asked to find, and we just found it. Now, I want you to try one. This one is in terms of, it's a function of three variables. So let's try it. So once you try this, so I want you to find the potential function of the conservative vector field f is equal to y squared 2xy plus e to the 3z, and then 3y e to the 3z. So it's something similar to what we've done. All you have to do is to take three integrals in this case. And remember, when you take the when you take the integral with respect to x, for instance, integral dx, your constant will be a function of y and z. Okay, so it will be of c of yz. And then when you do the integral with respect to y, your constant will be d of xz. Then you try again, your constant will be maybe e of capital E of xy or something like that. All right. And then you go from there and do your comparison. Okay. We're going to state another theorem that is going to be very, very important to us. This is the fundamental theorem for line integral. Fundamental theorem for line integral. This theorem says that if f is a continuous vector field, on an open interval, or let's say on an open connected region. How about that? It's open and it's connected region in R2 or R3. Then there exists a potential function with f equals a potential function, the function is phi, with f equals the gradient of phi, if and only if the following is true. If and only if one, the integral line integral f dot t ds is equal to, which is equal to the line integral f dot dr. We talked about this in section 2. Phi of b minus phi of a, where c, for all curves with endpoints A and B in an open region, in the open region, okay? Then the closed integral dr is equal to 0 for all simple closed oriented curves in the region. Okay. So fundamental theorem of for line integral, f is continuous. It's a continuous vector field in an open region. Okay. So the main thing to take away from this theorem is that f is conservative. F is conservative if and only if this is true, right? And that is true. In other words, another way to use this theorem is if you can show that f is conservative, right? Then a quick way of computing this line integral is to just plug in b and a into the potential function, right? And if your line integral is along a curve that is closed and oriented, then the line integral will be equal to 0. Okay? So here our C, in this case, our C is a curve that starts from point A and ends at point B. Okay. So all you need to do is plug in A and B. And when I say point A, it could be that R of A could be R of T at that point. Okay. Actually, A and B are just points. Actually. All right. And what else can I say? I can't say a whole lot more without going into an example. And I want this video to be short. So we're going to discuss this more in class. How about that? Okay. So I'll make a note for myself here that we're going to do more examples. I'll show you examples. Examples will be done in class. I will see you